So given this observation, how do we, solve for a particular, how do we solve for a particular system? So one of the things that you have to do is that, first you make a guess about the energy. And the nice thing is that you can automate these you can actually write a program which will do this. So you don't have to do it like, by hand. You can actually program this. And then based on that guess, propose a trial wave function that satisfies the above observations, as well as the boundary conditions. Okay, so let's see some examples. So, for example, suppose we have a square potential well, and we want to find the ground state. Other states can also be found, and we'll see that. So we have a square potential well, and we have some ground. And suppose that you say, okay, let me just take 4 random guesses. This is EA, this is EB, this is EC, and this is, say, ED. Okay, so this is EA and EB, EC, and ED. These are guesses. So if you make these guesses, then you have to, you will find the, let's look at psi A. So I'm going to make a copy of this. So psi A is going to be, because what will happen is that because the energy is pretty high, the curvature of the wave function will be pretty high. So the curvature will go to 0 very rapidly and then, it'll curve towards the x-axis. But when it goes beyond this region, it goes to region 2. And when it goes to region 2, it curves away from the x-axis, right? And here we see that we get a wave function which is going to be diverging at infinity, right? So this is, that means that this, this is not a good guess. Now, similarly, if I do EC and ED, so this is, say, psi of A. Okay. Now, if I do EC and ED, the problem there is, the curvature is not very, it's going to have a very light curvature because the energy is small. So the curvature is going to be like this and like this. And then yeah. And then what happens is that when it hits, this x-axis, it's psi is going to 0, but psi prime is not going to 0. Okay, so it's not going to go to 0. So it's going to go through, and as it goes through, it just goes like this. Okay. Similarly, as it goes here, so again, we have a problem, right? And similarly, if you have for other values, small values of x, another thing that can happen is as follows. Can just go like this, and then it curves away from the x-axis even before it reaches the x-axis. Okay, so it just goes like this. Okay, so that is also not going to work. So there's going to be some critical value. So you see that this is not easy to find something that satisfies all the boundary conditions. So for EB is the sweet spot, and there will be one where it just goes like this and hits a wave function which such that it actually goes to 0 at infinity. And that is the wave function that satisfies all the boundary conditions. And this will be the wave function that's going to be the valid wave function, okay? So this is how, yeah. So I think these are too large. This is too large. And EB is also too large. This is also too large. And this is too small, and this is just about right, okay? Okay, so this is a bit qualitative, but as you can see, these are things that you can automate using a computer. Okay, any questions? So these are things that you have to play with. If I give you some examples, you play with, and then you get the better idea. You get the idea about, okay, what is happening. Okay, so this is ground state. How do you find the excited states? So how do you find the excited states? It's very similar, except you have to take into account that for the nth state, you must have, say, n minus 1 nodes, right, of the wave function. So for example, if I were to do the n equals to 1, I could try several different things. So the way to start is to actually start with the intuition we had from the infinite potential well. In the infinite potential well, the n equals to 1 was like this. So in the infinite potential well, we just had to impose that the wave function was continuous at the boundary, right? We didn't have to impose the fact that its first derivative was continuous at the boundary. So this was the infinite potential case. And in that case, the wave function just needed to go to 0 at the boundaries. Its first derivative didn't have to go to 0. But when the finite potential well is concerned, if you have a discontinuity, the first derivative is also supposed to go to 0. So okay, so this is not the best drawing, but yeah.
Okay. Great.